So let's discuss some basics about fluid dynamics now. Okay, so here in this section we'll see three important things. Continuity, which is basically your conservation of mass. And then we'll see the energy equation, which is basically your Bernoulli equation. And then your impulse momentum equation. Well, this is useful for determining forces coming on the pipes, forces coming on the bends, all those things. Okay, so what we will do now is let's take continuity first and what it means. Let's derive a general equation, and then once these three topics are completed, then we'll solve some problems on this. Now, continuity. Well, in order to understand this, let's say the flow is taking place where the inlet section is this, outlet section is this. Now, I identify a control volume which is an enclosed. This is the dotted surface is my control volume. The fluid enters in this way, gets out in this way. So the general equation what I can write is sum of all the mass flow rates that enters inside is equal to mass flow rates that goes out plus some can increase, and whatever is staying will increase the mass of the control volume. So let's say mass of the control volume is mcv, so this is it. So other way of writing it is mass, sum of the mass that is coming in minus sum of the mass that is going out is equal to the increase in mass of the control volume. So this is a very general equation. Now you might be worried why mass of the control volume is increasing. Well, there might be cases. Let's see. Control volume is a volume of fixed, is a fixed volume. Okay, mass can increase. Well, because the shape, the shape can deform. Okay. Well, so there are two cases here. Cases one. First, you have a steady flow. So steady flow means mass of the control volume cannot change or doesn't change with time. Okay, so then in the general equation will become mass flow rate in is mass flow rate out. Okay, that is what is the equation for, that is what is basically the conservation of mass. Okay, now how do you find out mass flow rate if there is only one inlet? Let's say this is the inlet and the cross section is A. Now in time dt, the mass that is entering, let's say, has traveled dx. Okay, in time dt. So what is the normal velocity or the horizontal velocity? That is u dx by dt. The mass that has entered is area of cross, the volume of the mass that has entered is area of cross section into d. So this is the volume of the mass that has entered, and the mass that is associated with it, the mass that is associated with this volume is density into volume. So it is rho a dx is the mass that has entered. Now the mass flow rate will be the time in which it enters. So this dx, it has traveled in time dt. Now dx by dt is rho a u, which is the normal velocity, rho a u. So this is the general expression for the mass flow rate going through a section of cross section A. So rho a, most of the time AU we write as Q, which is the volume flow rate. So if you have many inlets, you have many rho Qs. So let's say for one inlet, the mass flow rate in is mass flow rate out, and that is the density to volume flow rate in is density into volume flow rate out. We assume that it's incompressible, densities are not changing, so volume flow rate in has to be equal to the volume flow rate out, or your A1, most of the time velocities we write A1 V1, so A1 V1 is equal to A2 V2. And if the flow is compressible, we will write, we'll consider the density variation also. So rho1 A1 V1 is rho2 A2 V2 if it is compressible, flow is compressible, densities are changing. And if it is incompressible, we write, so basically the mass flow rate for a steady state incompressible flow will just turn out to be A1 V1 is equal to A2 V2 of decreasing cross section. So whatever the volume flow rate that is entering, okay, now, so I mean this is a very simple case. Like you have a pipe, say, in your house, and what do you do? Let's say by your hand you try to just decrease the diameter to this, then the velocity of the water that comes out will be more than the velocity of the flow in the pipe. Because you have decreased the diameter, the flow rate, the volume flow rate has to match. So this velocity is more than the average velocity in the pipe. Okay, so that is just based on I mean, it's quite practical. Okay, so this is case 1. Case 2, steady flow. I mean, that was steady flow. Case 2, unsteady flow. Let's see. So if you have case 2 unsteady flow, or let's say the mass of the control volume is increasing or decreasing with respect to time. Now let me give you an example to understand this with respect to time. Okay, so let's take, you have a cycle tire, okay, and you are filling up the gas. Okay, you're pumping, I mean pumping the gas, applying the force, gas is going on. So this is your control volume, basically the space inside the tire is your control volume. Okay, okay, so now as you fill the air, you have the inlet, so mass inlet is there, no outlet, mass outlet is 0, mass inlet is there. But what is happening, the tire gets enlarged, the volume of the tire is increasing, so the mass of the control volume is increasing because you're pumping mass, you're pumping air into it, mass of the control volume. So that equation will become mass of the flow rate in minus mass flow rate out is mass flow rate. This is the general equation. This is 0. Okay, this is the general, this is 0. So whatever mass flow rate that is entering in will increase the mass flow rate of control volume. So in that case it becomes unsteady flow, and this is the example of this. You're pumping air in a bicycle tire. Okay, the other example, let's say you're drawing out some water from the tank which is already filled. Okay, you're drawing out some water from the tank. So water level is this. So this is my control volume. Okay, so if I draw out air, so in this case basically the mass of the control volume is decreasing. You don't have inlet, you have only outlet, you're drawing water. So mass outlet minus mass inlet is the equation. So this is 0, you don't have this, you're drawing out some mass, so that will lead to decrease in the mass of the control volume. So these are example. So the general expression is this: mass flow rate in is mass flow rate out is the increase in. This is the general equation. Apply for steady flow or unsteady flow. We have seen both the cases. Okay, so later we'll solve one problem on this. Most of the time it's steady flow. So let's see the second important topic in this, the Bernoulli equation or the energy equation for the fluid. Okay, so let's first derive this. Let's tell you the process in deriving, then you will be able to understand. So when a fluid is moving, let's say a fluid particle, consider a fluid particle. What are the forces? You have these pressure forces. Okay, the pressure forces are there. You have the shear forces because of viscosity, so let's call that as tau. So the pressure forces in its direction, okay, plus let's say the viscous forces in its direction, and whatever other forces you have, well, that is equal to mass into acceleration in its direction. Basically what you are doing is you're applying Newton's law in each direction. Well, similarly you can have the pressure forces in y, the viscous forces in y, you can have the gravitational forces in y. If you assume this is y, this is x, and this is z, it's just mass of the particle into acceleration in y. Similarly, the pressure forces in z, the viscous forces in z. So you're writing a general equation. General, okay, let me write gx here also, so that wherever you have gravity you will include, otherwise you will not include. These are the general forces. Now assumption number one, what we make, assumption number one, we assume that there are no viscous forces. So all your shear stresses are not there, so your viscous forces, which we are denoting by Fv y, Fv are not there. So we assume that, okay, and then if we just balance out the equations, okay, and the second assumption is that for Ax, Ay, we have already derived the equations in the fluid kinematics. Like for Ax, you have dou u by dou t plus dou u by dou x into u plus dou u by dou y into v plus dou u by dou z into w. Similarly, you have for a, ay, and az. So I'm just telling you what are the assumptions which go in order to derive Bernoulli's equation. Dou v by dou x into u plus dou v by dou y into v plus dou v by dou z into w. So these are the equations which we derive for. Okay, so now you have to use these equations at the back, and because the flow is non-viscous, it's irrotational. Okay, and so if it is irrotational, your curl of velocity vector is 0, and you get three equations from them. What are those equations? Dou u by dou x, dou u by dou y is dou v by dou x, that is one equation. Then your dou u by dou z is dou w by dou x, that is another equation. So you have three equations by curl of v, and then you have dou v by dou y, dou v by dou z is basically dou w by dou y. So that is third equation. So if you substitute all these three, so all these combined, if you substitute in this Newton law, you get something called this equation: v by rho by v square by 2g plus height z1 is equal to constant. So this is a general equation. This says that this quantity will remain constant at any point in the, at any 2 points in the flow. This quantity will be constant. So here v is the total velocity. I'm taking all the components. Okay, so let me list out what are the assumptions and for what, under what cases it is valid. Assumptions that was derived here is the flow is ideal, that is non-viscous and irrotational. Basically, I mean, because of this shear stress only, we'll have the rotation component. So it's more or less, when I say non-viscous, it means it's irrotational, and the flow is incompressible. We have not assumed that density is varying. Okay, so this is, that is this, so that is derived under this condition. So Bernoulli equation. Okay, so these are the basic assumptions. So if my flow is real, that is because real fluid will have viscosity, so then when I apply that equation, it just turns out to be this: v1 square by z1 is equal to So at 2 points, somewhere at the 2 points here and here, and you're applying. So this is the case for ideal fluid. The term is constant. This is equal to this. But for real fluid, this is not constant, and you have something called head loss. Head loss, which comes because of the viscosity. Okay, this is the real fluid. Okay, now each term in this equation, so if let's try to understand deeply what happens. It's constant. So this term is the pressure head term. Each has a unit of meter, so it's a pressure head. And this is your velocity head, and this is the gravity head or the potential head. So some of these three heads are constant. Okay, so that's what Bernoulli's equation says. Okay, so later when we'll solve some problems, we'll try to understand what is the significance of each term. So the decrease in one of the term will lead to increase in another term. Okay, so now let's apply one of the application of Bernoulli equation is Venturi meter. So Venturi meter is a device which is used to measure flow rates in pipes. So you want to measure how much flow rate is going in a pipe. Well, what you do is you have a pipe. Okay, somewhere you connect something called Venturi meter, which has a convergence section and a divergence section. Okay, so you have point 1 here, point 2 here, and then again bringing back to the normal pipe. So 2 diameters, and flow is taking place in this. So we assume that if the flow is ideal flow, and we can apply Bernoulli's equation. So P1 by rho g, it's at the same height, so the jet term will not come, is equal to P2 by rho g plus V2 square by 2g. So now these area of cross sections, I know this is A1, this is A2. So the volume flow rates we already saw in terms of area of cross section is constant. A1 is equal to A2 V2. So what I will do is I can represent A1. Okay, so velocity V2 is more. So let's write P1, bring out the present terms on this side. P1 minus P2 by 2g is V2 square minus V1 square by 2g. V2 I can express in terms of Q, because Q is ultimately what we want, is 1 by A2 square minus 1 by A1 square. So this is P1 minus P2 by rho g. Let's say the pressure difference, you got the pressure difference. Now this pressure difference you can just measure it by connecting it to some kind of a manometer, which you already seen how manometer works. So the pressure difference at 1 and 2 you can get from manometer, that is H. Okay, so from this I can write, from this equation, Q square by 2g is A1 square minus A2 square by A2 square is equal to H, and this value comes out to be, after simplification, A1 A2 root 2gh by root over A1 square minus A2 square. So by just application of Bernoulli equation between section 1 and 2, and by your continuity equation, that is volume flow rates are same, you can get a general equation which just depends on the area of cross sections. So area of cross sections, you know the dias and the pipes is circular, so A1 A2s are all pi 1 pi by 4 d1 square, and A2 is pi by 4 d2 square. So you can get the area of cross section, and this H is basically the pressure difference which you can measure by manometer. So this you would have done in your lab, Venturi meter. So only thing what you need to know is A1, A2 and H. H is the manometer reading. From there get the H, which measures the pressure difference. A1, A2 already you know the dash. So this is a very simple device to measure the volume flow rate, and it works on Bernoulli's equation. So just try to understand when Bernoulli's equation is valid. So let's now discuss the impulse momentum equations. Okay, so let's say you have a pipe somewhere like this. Okay, and this is the section 1 and this is the section 2 this is your X, this is your Y, and okay, let's say a 2D flow is happening. So now from your, let's start from scratch. This is your Newton's law in its direction. So what it means is summation of all the forces is mass into acceleration. Well, mass, you can write acceleration in dvx by dt, and you send dt that side, you get m dvx. Okay, you get m dvx. So what we do is, this is what is the beginning of your impulse momentum principle. That is, this, the left side is called impulse and the right side is called change in momentum. In terms of fluid, we do it in a different way. What we do is sigma fx, this entire quantity is represented like this mass by dt. Okay, once you apply all that control volume system approach, everything, what we get is the rho q is mass flow rate into final velocity at the section 2 minus initial velocity in section in the same direction. So basically you can just understand that it is mass by time becomes mass flow rate, and the change in the velocity is v2x minus v1x. So this is the force that is acting on the fluid between section 1 and 2. Okay, and similarly in the other direction, the force that is acting is mass flow rate v2y minus v2 v1y. That is the component of the velocity at the section 2 in the vertical direction minus the component of the velocity at the section 1 in the vertical direction. The change in that gives you the force. And if you have z direction, well, let's write down for z. Okay, so these are your impulse momentum equation. Okay, now m dot is always your rho q, the density into volume flow rate. So these equations are basically useful in determining the resultant force that is acting on the pipe. Resultant forces exerted on the boundaries of the flow So what you have to do is, you have to basically take this fluid, and let's say this fluid is something like this. So now what are the forces? The pipe will be exerting, the entire pipe surface will be exerting some force. You have this pressure from the fluid. So all that forces, summation of all those forces is this in x and y directions. So you can get the forces which are exerted by the pipe surface on the fluid, or the other way, the forces exerted by the fluid on the pipe surface. Okay, so example being force, finding forces, because once you find the forces you can support those pipe. So finding forces on a elbow or bend. So this is what these equations. So we have seen three equations and their significance, and then we'll solve some problems involving these three concepts, because these three concepts are very important. Most of the problems you can solve with these three concepts. So we'll apply these and solving some problems.